Good afternoon, everyone. I'm very happy to be here today to talk to you about Clangd. So today we're going to talk a bit about Clangd in general. So what's new since the last developer meeting. So it's going to be a bit of an update. Also, what is Clangd in case you don't know Clangd. And then we're going to go a bit deeper into the proposed indexing infrastructure. And then you'll see it's like solving similar problem that the index while building solution presented before is solving. So there's definitely some things we'll have to put in common. Yeah, we're going to talk about the current state, all the features that are supported and being worked on. And we'll talk about the future challenges and possible collaborations. So about me, I'm Marc-Andre Laperle. I work at Ericsson. I've been working there for a few years. I was working a lot in the Eclipse community before, specifically in CDT, which is the C and C++ support. And now I'm kind of a newish Clang contributor since the beginning of this year. And I'm pretty enthusiastic about C and C++ tooling and IDEs, etc. But I'm not a compiler expert, but maybe soon. So what is Clangd? In case you don't know what it is, it's a tool in the Clang extras repo. Its goal is to implement the language server protocol, often called the LSP, specifically for C and C++. So this protocol goal is to implement all the language smartness features in IDEs. So things like code completion, find references, and open definition. So it puts it into a protocol in JSON RPC. So any client can talk to any language server to support many different languages. So it's a good way to kind of mix and match languages and clients. So we regularly test Clangd with Visual Studio Code because this is where the language server protocol was born. So there's a good client library there to test things. I also test regularly with Thea, which is an IDE we are working on at Ericsson with other companies, and also with Eclipse. And I'm hoping that we can add more like Vim and Emacs because they're also very popular even inside Ericsson. So this is just to illustrate a little bit how it works when you use an editor and a language server. So on one side you have the tool, so you can have a VS Code, or Eclipse, something like that. And then on the other side you have your language server, and in this case here it's Clangd. So whenever a user opens a document, then a message is sent from the tool to the server to notify that a document has been opened. So then at that point, the server can start parsing the file, maybe loading some caches, so that it's ready to process other requests from the user, like code completion, for example. And then whenever the user edits the file, then another message is sent from the client to the server, and then there again, the server can update, reparse, or update its caches. And from the server to the client, it can send messages as well. So it can send diagnostics, which is basically errors and warnings. So you can get errors and warnings as you type for a very quick feedback. So the big value of this protocol is that everyone kind of agrees on this protocol. So you can really mix and match languages and editors. Oh, I have the clicker. So the current status of Clangd. So here in this table, you have the features, and there's a column to say whether or not it's supported in the protocol, whether or not it's specified in the protocol, and whether or not it's implemented in Clangd. So you have a lot of very useful things already, like formatting, code completion, diagnostics. So it's already very useful to assist you programming, and then when you compile, you're pretty sure everything will compile because you already have diagnostics from Clang. We have some go-to-definition support, but it's actually going to the declaration because we don't have an index upstream yet, and we'll talk a bit more about that later. And we have things that are very close to being done, like source hover and document highlights. And you see in this table, there are a few of them that are not possible right now because we don't have the index upstreamed yet. And then there's quite a bit of features that are not specified in the protocol that we would like to see in Clangd. And it's not 100% clear if this should be specified in the protocol because the language server protocol is meant to be kind of language agnostic and kind of a lightweight protocol. So those are things that we will try to propose in the protocol, but for sure we want in Clangd either as an extension to the protocol. And it's pretty easy to extend the protocol because it's just some JSON RPC messages, so you can just add some, and as long as the clients and the server agrees on it, then it works great. So what's new since the last developer meeting? There was a lot of improvement in code completion, so it gives much better results, much more detailed information about all the completion items. You have code snippet support, and it's also much faster, so you can do code completion really more quickly. Even like reparsing the file and getting code completion is much faster. You can go to declaration, so that was done quickly after the developer meeting last time. You can do a signature help, so as you are typing parameters for your function call, you will get a little pop-up that will tell you what the parameter types are, etc. So that's very useful. And there's a very small extension that allows you to switch between the source file and the header. And you might be wondering, why did we put this in Clangd? It's so simple because it's just based on the file name. So right now it's based on the file name. So if you have foo.h, it will switch to foo.c. But later when we have the index, even if your files are not named the same, we will use the index to figure out where the definitions are for a given declaration. So we can find the corresponding source file. And as well, there are now more command line options. So you can set the Clang resource directory, for example. And you can also now set the path to the compilation database. The compilation database, if you don't know what it is, it's a JSON file that contains all the compiler arguments that were used to compile your program for all source files. So Clang can use that file to figure out which includes and which macros to use when parsing the file. So it's important to be able to find this file so that Clangd can parse files properly. There's also been a lot of performance improvements. So now there are multiple thread workers. So you can open multiple files at the same time. It will parse at the same time. So this is much better. There's a better preamble management. So as I was saying, this is important if you want to get quick results for code completion. And anytime you modify the file, you don't necessarily want to reparse all the included headers. So if you can cache that, then it's much faster. And there was a lot of bug fixes and re-architecturing and cleanups. So it's all very good and promising. And the community is really growing fast. There's maybe 4 or 5 people that are very regularly working on it. It doesn't sound like a huge number, but it's actually not that much code Clangd, so it's actually very good. And there's also more people that are more occasional contributors. So I think it's a very good number and it's progressing pretty well. So indexing. So in case you don't know why we want to do this, for example, here, if you have a main.cpp file that includes a foo.h header with a declaration to foo, and then you have a call to foo. So if you open that main.cpp file in an editor and Clang parses it, it can very easily find where that foo was declared. So that's not a problem. But when you want to actually find where foo was defined, which is very often what the programmers wants to do, then you somehow need to know about foo.cpp and the location of foo. So one way you could do it is when the user wants to find a declaration of foo, then reparse all the source files and then find it. But this is way too slow. You need some sort of database of where all the symbols are defined. So this is why we need indexing. So we've started working on a language server even before Clangd was kind of proposed recently. So the first prototype was actually just a very small project in the Git repository. It was really at the stage of experimenting with code completion in Clang, using the AST visitors and then parsing the JSON. So that was very bare bone, and at Ericsson, in my team, we were very new at using Clang, so that was a good way to get up to speed with what we could do. And then on a mailing list, it was communicated that people wanted to work on the Clangd and support the LSP in the Clang repository. So that was the perfect opportunity for us to join forces and work on that. So we migrated kind of our prototype code to the Clang code base, but we started off in a branch because we wanted to start this bigger feature of indexing. So at that point, Clangd was using LLVM's YAML parser for JSON instead of the one we were using in our prototype, which was a libjson CBP. And the JSON RPC was kind of a handwritten, but it's not a very big part, so that's not a big problem. And when we migrated to Clangd, then we already had the open declaration feature working, because, as I said, it's very easy because Clang already knows where it is with the includes. So that was a pretty easy feature to do. And at that point, we were not reusing any of the Clang index component code. So we were really kind of manually visiting the AST. So that was not the best solution. So a bit later, so yeah, those prototypes have numbers, but it's not really how it went, but just a way to think about them. So we wanted to introduce the notion of persistence, so really having a database so we can actually find the definition of the function. We were still using the AST visitor to find where the user was pointing at, so to figure out what you wanted to jump to, which is still not the perfect solution. But we started using some Clang index code, a class called index.dataConsumer that can be used to feed the index. So that's super handy because it figures out, it walks the AST for you, and then there's a callback to handle the symbol occurrence. So you can just store that in the index and then carry on. So at first we didn't really have a file format for that. Just to get things started, we came up with this very awesome, simple, very slow index file format. So it's SVSI file format. It's really just a linear dump of things, so I'll show you a bit the layout after if you're curious. At that point, there was no definition and headers and handled because you kind of have to track to make sure you don't duplicate them. So at that point, we just decided to deal with function in source files. So the format of the SVSI file is very simple. It was just dumping the number of files and then the name of the file and then the number of symbols and the name of the symbol and then so on, more symbols, more files. So it's very slow. If you need the symbol at the end of the file, then you need to read the whole file. If you change any of the files, you have to rebuild the whole file. So that was terrible, but everything, we could connect all the dots and kind of have a working prototype. So the first thing we want to improve after that is making a better format, a better way to save data. So then we figured out that we could reuse the same code to actually find where the user was pointing with the cursor as the code we were using to feed the index. So there was a lot of more code reuse. So that was good. And at this point, we actually upstream that cleaned up code to have an open declaration already in Clangd. And then we started to replace the file format with a new class called index data storage. And this was very much inspired from Eclipse CDT's database. And I'll explain a little bit how this works later. But it's basically a malloc-like interface to writing and reading to a file, so it's very flexible. We also introduced a Btree so we can find things in logarithmic time. So we can find file entries or symbols much faster. And so at this point, we were not dealing really with definition headers, just going step by step. And we started handling events for source file changes, but not headers. We started tracking dependencies of files. So if for a given header, we tracked which files actually included this header. With this information, this allowed us to figure out when a user opens a header in the editor, we actually didn't know which compile arguments were used in the context of this header because the compilation database, the JSON file I mentioned before, only has entries for source files. So with this dependency information, we could actually figure out which source file includes this header and then find an entry in the compilation database. So now we were able to open header file properly in editors and then get proper diagnostic and completion. So that was already a good improvement. So how does the index data storage work? So it's quite different from the index file building solution. So yeah, it's a malloc-like interface to writing to a file. It can store just bytes, and there's also some helpers to store integers, strings, and more importantly, you can store pointers. So you can do very complex structures and persist it to disk. So you can do like linked list or any kind of weird data structure you would do normally in memory. And it was very inspired from Eclipse CDT database because we worked a lot with this before, so we tried to reuse a similar strategy, but it doesn't mean that it has to be the ultimate solution for this problem. What does it look like in terms of layout? You just have a simplified version in case the format changes, so you can rebuild it. And then you have a table of linked lists to free blocks of a given size. So when the user allocates data in the file, it creates a data block, and then when the data block is freed, it's converted to a free block. And that free block, depending on the size, is then inserted into a list of free blocks for later. So whenever you do a new malloc and you need a free block to allocate memory, then it looks in the free list, in the list of free blocks for available blocks to reuse. So it's a pretty simple layout. But it's pretty flexible, so you can really store any kind of data, really any kind of bytes you want. So it differs a little bit from the index file building in that you have one file that contains all the information. So it's not multiple files that then you query. It's just one file that has many pointers inside it. So it's a bit different. There's a caching mechanism, so you can also think of this file as 4K pieces. So whenever you want some data in the database, depending on the offset, it will figure out what's the piece ID it needs, and then it will fetch that piece ID, that piece, and put it on the cache. And the size of the cache is configurable, so we can make sure that Clangd doesn't use a huge amount of memory. We can configure that cache to any size we want. And then the Btree is a pretty classic Btree. It's a tree with nodes that contain multiple children, and it's a balanced tree. And you can do logarithmic insertion, search, and deletion. Deletion is a bit more complicated, but it works. So that helped a lot making the index faster compared to the very slow index file. And the keys in the Btree are actually pointers inside the data storage. And the nodes themselves are just data inside all the same file. So the tree itself is very lightweight. It just points to other objects in the database, which are themselves much bigger. So here, in the previous slide, I had put like A, B, C, D, E, F. You can think of them as file names, for example. And here, we're pointing to actual file entries in the database, which can contain more data like the occurrences, et cetera, et cetera. So we can use that to quickly find a file in our database and then get its occurrences. So now that we have a better persistent mechanism, we wanted to add some of the missing things that I've mentioned before. So for example, we were not really tracking when header files changed and things like that. So for that, we started adding timestamps to know what was the time at which we indexed the files. So we know that when Clangd restarts, we need to re-index them or not. And then whenever a header changes, now we do use the dependency graph to re-index all the source files that are dependent on the header. And now, not just definitions are stored in the index, declarations and references as well. And also everything in the headers are also included in the index, although the headers are only indexed once. So the first time it's encountered, it's parsed, and its symbols and occurrences are stored once. So that's something that could be improved. And the index model was changed to be a bit closer to the index while building proposal, so that we're slowly converging towards something similar. So at this point, we have the open definition and find references working. But I tried to cram so much new things for the conference that I haven't had the time to fix all the stability bugs. So it actually crashes sometimes when indexing Clangd. So eventually I will fix this. Okay. What does the model look like? So this is all in one file. So you would start at the lower left. So you have the Clangd index interface. So this contains access to a Btree of files and a Btree of symbols. So if you're interested in finding the definition of a symbol, then you use the USR, which is the Unified Symbol Resolution. So it's kind of as it was explained before, it's kind of a unique identifier in the index to find symbol and be able to do navigation across units. So you use the USR to find the symbol you're interested in the database. And then you can go through the occurrences of the symbol because the Clang index symbols contains a linked list of all its occurrences. So as you go through the linked list of occurrences, you search for the occurrence that has a role that's definition. So this sounds like a lot of work in computation, but it's actually very fast because things are cached in 4K pieces, and it's actually just in one file. So it's quite good. And then the Btree of files, if you go back to the lower left, you use it if a file changes, then you find the file entry in the Btree, and then you get all the occurrences in the file, and then you delete them because the user might have offset all the occurrences in the file, so you kind of have to rebuild all those occurrences. And then if it happens that you're deleting an occurrence for a symbol that has no occurrences anymore, then we delete the symbol. It's kind of a reference counting mechanism at the same time. So everything gets cleared and the memory is freed in the database. So I'm going to do a quick demo. I just want to show you the integration in the IDEs. So this is, can you see it? No, sorry. Okay, this is better. Okay, so this is the Thea IDE, and you can see I opened it in my browser. So it looks just like a normal IDE, except the backend could be running, I don't know, in Australia. So here I have the Clangd indexing code, and now because of the index, I can find all the references to vector. You can see it's very fast. I have 384 references to std vector, and of course this is not an index of all LLVM codebase. I just picked the Clangd codebase and all of its headers, but it's still quite a bit of headers and definitions, and it's pretty fast. You can find all the std vectors very quickly. Then sorry. Okay, so now here I have a method called to put raw record pointer. It doesn't matter what it does, but now I can control click on it and actually jump to definition of this symbol instead of jumping to the declaration. So that was not possible before without the index. So it's a good improvement. So this was in TIA, but because Clangd uses the language server protocol, any IDE that supports this protocol, it's very easy to integrate Clangd and get similar results. So here in VS Code, I can do find all references and I get the same results. And the amount of code in VS Code is really very tiny. It just says whenever I open a C++ file, start Clangd. So it's almost nothing. Same thing in Eclipse. I can find all references here, and it works the same, except this weird to-do label, but that's not my code. Yeah, so that's just a quick demo to give you an idea of how nice it is to be able to plug this in any IDE. So some of the challenges we have worked more on modeling the index and making it persisted on disk, and not so much on the actual indexing time. But for sure, the lack of header caching is going to be a major issue. So every time we parse a source file, if it includes string.h many times in the codebase, and we'll reparse it again and again and again. So there are possible solutions for this. We haven't looked so much into it yet, but it should be possible to use maybe precompile headers or pre-tokenized headers, or maybe the modules in Clang. So there are several ways we could try to fix this. And one problem is that a given include can be when you include the header, it can be in a very different context. So we have to make sure that it's still valid to use the cache information even though it's in a different context. So we might need some heuristic to, even if it's not exactly the same context, so different macros are defined, and maybe we'll have to be like, okay, maybe we'll let it pass and it will be not quite as accurate, but it will be faster at least. So there's some ways maybe we can try to introduce some heuristics. Maybe also we could make the indexing in multiple phases. So maybe index all the top level functions and not index the bodies of the function, and then do a second pass to get all the references in the body of functions, things like that. So at least the user could get some functionality, and then while the longer indexing finishes, then and when it's fully finished, then all the functionality will be there. Other challenges, we have to watch for all the possible file events. So on Linux, you would use maybe inotify to know if a file changed and if you need to reindex. But if you have a really large source base, like even LLVM, then you're going to run out of you're going to go above the maximum that inotify allows you to go. So right now we rely on the clients to send Clang the file events, but the problem is that we need to be able to go beyond this maximum, and we also need to watch for changes for system includes. So it's not so much I think the responsibility of the client, but the server will start to have Clang will have to start having to watch all the files itself, and maybe we'll have to spawn multiple processes to work around the problem with the large number of files. So that's kind of an open question. There's a lot of opportunities for collaboration. So as you saw just before this presentation, the index while building feature in Xcode 9, I think most likely could be reused and maybe even replace entirely the index storage that we're using in Clangd. I think it would be good if we put some background indexing code in Clangd that maybe we can move it from Clangd to the more common Clang indexing code instead of just Clangd, so others could use it. So other interfaces than Clangd could use it. One thing we'd like to support is also making the index extensible so that other tools for static analysis could add information to each symbol or each occurrences so that they can use the same format without having to have their own. We've also experimented with LMDB for doing the symbol mapping, similar to what Xcode is doing. And there's an open question about whether or not it will be possible to integrate that library, that external library, into the Clang code base. So refactoring, we're really interested in refactoring. One challenge will be if we want to put it in the protocol, we have to somehow specify it well enough that it can support other languages and enough options, but not too many. And so that's just the protocol itself is a challenge. And also making use of the refactoring framework introduced with Xcode 9, I think it's a really good opportunity. And we really want to add more refactorings and code generations. And so that's a very good opportunity for collaborating with people working on Xcode. And the quick assist support was kind of a feature in Eclipse that even when you don't have errors, you can do Control-1 and then start modifying some code, so maybe inverting conditions and things like that. So it's a bit related to refactoring, and we want to work on this as well. So I put some references in case you're interested in Clangd itself, or the protocol, or the Thea IDE that we've been working on. So, there's some time for questions. Thank you.
Hi, 2 questions.
Yes.
Do you work on Windows?
Depends on the day. Linux, Mac, and sometimes Windows. Why?
Well, I mean, like, Clangd, does it work on Windows?
Oh, Clang. Oh, does it work on Windows? That's the question. Sorry. I haven't tested recently, but that's definitely the goal, to make it work on Windows.
I see. And the second question is, how well do you do with like templates? I mean, like, if I got a template type and I call some methods on instances which are not immediately obvious what the type is, like, will you be able to find all the symbols that I actually mean?
So far, I haven't seen problems in this situation, but I suppose it could be some weird cases. And we're relying on the Clang index component codes to get the occurrences, and so far it's been looking pretty good. But of course, we could do more testing on that front to find some more edge cases. But.
Hello.
Hello.
So I was just curious, in terms of your persistence layer, the kind of first thought that came to me was like using something like RocksDB or something in the kind of LevelDB family instead of building a persistence layer from scratch. Like, what were your thoughts about that?
Which kind of DB, sorry?
Like RocksDB or LevelDB, something in that family. BerkeleyDB, there's all these kind of different persistent key value stores that people have built and optimized. And
I don't know those specifically, but LMDB, I think, would be a good candidate to replace what we had in the prototype. So definitely, we're open to reusing instead of having our own stuff. And
we can chat offline.
Yeah. I'm not afraid to dump some code and reuse instead. So.
Okay. Any more questions? Then thanks again.
Thank you.